All right, folks, let's take a look at exam 2 practice. So if we think about number 1, haloalkanes participated in several different types of reactions. So if we think about drawing 3-chloro-2-methylpentane, the first thing we have to make sure is that we're drawing our longest carbon chain. And then we want to make sure that we can number that appropriately. And remember, that has to be the lowest overall possible numbering scheme. And then we want to be able to identify our leaving group, which in this case is the chlorine, because its electronegativity allows it to be a little bit more stable. Then, right, if we think about drawing 2 enantiomers and 2 diastereomers of 3-chloro-2-methylpentane, we can actually think about how their orientation in space might be different. So here, right, we have a wedge and a dash. Right? Notice I only have one stereocenter though, because even though these are wedges and dashes, they're both still methyls. So this is S3-chloro-2-methylpentane and R3-chloro-2-methylpentane. So can't draw 2 diastereomers because we only have one chiral center. So the next question is, how would 3-chloro-2-methylpentane react with sodium ethoxide? So there are a couple of ways we can think about this. I gave you 2 different examples. So there's sodium ethoxide, and then there's the comparison if it were to occur with a hydroxide group, just so you can see the difference. But really, remember, sodium ethoxide is going to be both a strong base and a strong nucleophile. When it's a strong nucleophile, sodium ethoxide is going to attack and then kick out the chlorine as a leaving group in a concerted fashion. That's going to form a substituted product via an SN2 mechanism. If it's an SN1 mechanism, chlorine leaves on its own, form a secondary carbocation, and then my nucleophile attacks. Notice the difference here is I have an inverted product for my SN2, whereas I have racemic products for SN1, which means I have both the wedge and the dash for the substituted products. If my ethoxide functions as a base, then it's going to abstract a proton, and remember, I form the most substituted double bond, and this can occur via either E2 or E1. If I think about the evidence that I'm providing, that's the leaving group is my chlorine. I have a secondary carbon, so that means it can be SN1, E1, SN2, E2. All of those are possible options. And then my sodium ethoxide is a great or strong nucleophile. It's also a strong base. And remember, things like SN2 equals inversion and SN1 is racemic. And then if I had sodium hydroxide, it would form an alcohol. If it was sodium ethoxide, it's going to form an ether, just so you could see that contrast. Hi, sorry, I'm in the middle of recording. So I will happily help you in just a minute. All right, let's wrap up for problem 2. The formation and reaction of double bonds is significant in many contexts. So let's think about how we could name this molecule. So we want to make sure that we're paying attention to cis or trans, and E or Z, as well as R and S. So when we think about this molecule, we can always number our longest carbons. Right? We want to make sure that our double bond, we identify its position unless it's at the 1 position. And then we want to make sure that we identify both the R as well as the E, right, for our highest priority substituents. So this is what makes it E, or Entgegen. If I think about this molecule, it's 1-ethyl, 4-methyl, cyclohexene. And again, because this is the 1 position for my double bond, I don't actually have to worry about that as much. If I'm thinking about drawing a reasonable complete mechanism for my understand, I first want to recognize that my double bond is my nucleophile, my Br2 is my electrophile, and then I'm going to form a carbocation, and then I'm going to form this special bromonium species where it's strained, and because of that strain, my bromine can come in and kick open, but remember, they're on opposite sides. So one is up and the other is down. Doesn't matter which, but they have to be on opposite sides of this bond. And so my evidence here is that I have a partial positive and partial negative on bromine. I can form a carbocation on the tertiary carbon, and then I form a bromonium ion. And then bromide is going to attack as a nucleophile, and the opposite stereochemistry for a product, so this is anti-Markovnikov. And so if I think about another mechanism, so in this case, this is the apply, right? How do water and sulfuric acid react with the following molecule? The first thing I have to think about is that my sulfuric acid is going to be my electrophile. My double bond is my nucleophile. It's going to take that hydrogen. Then I'm forming a carbocation, and it's water that attacks that carbocation. Finally, my HSO4 minus acts as a base to pull off the acidic proton, and that is going to generate a racemic product. So we have a couple of things. My double bond is a lone pair in disguise. That's what makes it a nucleophile. It attacks the acidic proton on H2SO4, which can form HSO4-, my conjugate base, and a tertiary carbocation. So the most stable, right, is the already formed carbocation because it's tertiary carbocation. So there's no methyl or proton shifts that can occur. Water is a moderate nucleophile. And then my HSO4- is a conjugate base, takes this acidic proton from the water and forms a hydroxyl group. Note, I want to make sure that I identify that it's a racemic product. Just give me a second. So if I think about problem 3, I want to make sure that I can identify all of my functional groups containing oxygen. That's something that we always have to be aware of. And those are going to be helpful as we're thinking about drawing mechanisms. And then for the following alcohols, we're going to indicate the type of carbon that the hydroxyl group is bound to. So this is a primary, this is a tertiary, this is a secondary. And then part B is to draw each of the products that the alcohols reacted with HCl. And remember, this is through a substitution reaction because Cl- isn't a particularly good base. And then we talked in class when we were looking at lecture 13 specifically about drawing a reasonable and complete mechanism. And so the idea here is the alcohol is going to attack thionyl chloride. Chloride is a good leaving group. Pyridine attacks the sulfur. And so this generates, right, a great leaving group. So then another chloride leaves. The sulfur pyridine is now a phenomenal leaving group. And so my chloride ion can then attack, displacing the pyridine leaving group. So that's the mechanism that I draw here. And remember, we talked in class about how I might give you a mechanism and ask you to explain it. This is a good example of one that I would give you and ask you to explain. For question number 4, you're going to draw the following molecule and state whether it's going to undergo SN1 or SN2. I noticed my bromine is attached to a tertiary carbon, so that means it has to be SN1, and so it's my most stable carbocation. For number 2, I have to draw a reasonable complete mechanism, so I need to draw this molecule. Think about the fact that I have a leaving group, but then I also have this ability to do a methyl shift to create a more stable carbocation, and then my bromine can reattack as a nucleophile, but it's going to form racemic products. So I have a secondary carbon with bromide, which is a good leaving group. This forms a secondary carbocation, which is not the most stable. So it's going to form a tertiary carbocation through a methyl shift. And then the bromide is a nucleophile, which can attack the carbocation, forming a racemic product. You can look in your notes and then also in the materials online for how to complete this table. But these are the most significant differences between SN2 and E2 and SN1 and E1. When we think about problem 5, this is one that we actually did in class on Tuesday, and we're pretty familiar now with drawing the structure of leucine at a given pH, and to be able to compare that structure to one at a different pH. So this is a relatively acidic pH, but notice I have deprotonated my carboxylic acid, whereas here this is a relatively basic pH, and I've deprotonated every available proton on my molecule. Note I've identified my net charges. You're familiar with being able to label the equilibrium reactions, and we actually went over how to sort these for the apply problem in class on Tuesday. For problem number 6, these are functional groups containing nitrogen, and remember this is what we talked about on Tuesday. So why are aromatic amines less alkaline than aliphatic amines? So aliphatic amines, the nitrogen is only bonded to alkyl groups, whereas in an aromatic amine, it's attached to conjugated pi bonds. So due to resonance, the aromatic amines are less basic than aliphatic amines. So for the neurotransmitters that are shown, choose one and draw the mechanism for the formation of an imine. So can't form an imine with any of these structures because I have to have a leaving group. And notice I only have hydrogens here. So in order for my lone pair on my nitrogen to come down, I have to have something that can leave. Then I could actually show the formation of an imine. So each of these molecules has an alpha carbon with 4 bonds and no leaving group. So that's the carbon that's nearest to my amine. So in order to form an imine, they would need a leaving group. Then the mechanism could proceed as shown. And then the last problem is we have several models to represent aromatic rings. So we're going to draw the resonance structures for benzene as well as the hybrid structure. And notice you can draw a reasonable and complete generic mechanism for your electrophilic aromatic substitution. There's extra help on this week's iLearn if you need some additional practice, but the idea here is your double bond attacks your electrophile, and then you can move your double bond around the ring. And then, of course, right, at the end, you're going to need some type of base to deprotonate your hydrogen and reform your double bond or reform your aromatic structure. And then you're going to apply this generic mechanism to any one of these examples of electrophilic aromatic substitution. Question number 8 is finding mistakes. So notice, remember, we can have no pentavalent carbons. Here, I'm missing a carbon, so make sure that you pay attention to your structures and don't leave anything behind. Make sure that you draw complete Lewis structures, including formal charges and lone pairs. And then here, make sure you're paying attention to stereochemistry, cis, and say, for example, the assignment using con-angle prelog of your R and S, and notice, right, where your stereocenters are. And then here, right, for a reaction mechanism like an oxide, we need to make sure that we draw in any missing stereochemistry. So hopefully this helps as you're thinking about how to solve these problems. If you have any questions, please don't hesitate to email. And good luck studying for the exam.